Hey there, it's Jason Gorman from Codemanship with a video about continuous inspection for Java teams. Now, if you're working on a team and maybe you're using Git or GitHub, possibly you're working on developer branches or feature branches, and you have a kind of Git flow for when you need to check in your changes that includes submitting a pull request, so that your changes aren't merged automatically into the trunk, into the main branch. There's what we call a quality gate that it has to jump over first in order to be accepted into the code base. So we're going to talk about this idea of quality gates, and in particular where it comes to code inspections. So typically with a pull request, the idea is that your changes are then reviewed by someone else on the team or by an architect or some kind of technical authority. And only if they pass that test, only if they pass muster, do your changes make it into the code. And if there's any problems, you need to fix those first and then resubmit. And that's great. I think it's a really good idea that code should be checked before it becomes part of the shared code base. But code reviews, code inspections they're a form of testing, and they're a form of manual testing. And the problem, as we've discovered with manual testing, is that it's too slow. And also it misses a lot of stuff as well because it's too slow. So when we ask people to review our code, it's going to take time. We're going to have to wait for them to read the code. We're going to have to wait for them to become available to read the code. Maybe they're busy doing something else. So that can become a bottleneck in our delivery process. That can slow down the process of integrating. So continuous integration with pull requests can be tricky. And I see a lot of teams who have that bottleneck. But also it misses a lot of stuff. Asking someone to read your code, we're relying on that person spotting all of the issues that need to be spotted. And it's a similar kind of thing with pair programming. I'm a big fan of pair programming, and there's a lot of evidence to suggest that it does significantly improve the quality of code, because two pairs of eyes, having someone else watching what you're doing as you're typing, they're likely to spot things that you're not spotting. So less stuff slips through the net, as it were. But stuff still slips through the net, and quite a lot of it, in fact. So what did we do with logical testing? When we tested the logic of our code to see if there were logical bugs in our code, to remove the bottleneck of manually testing it, well, we automated those tests. Speeds up the whole process, but it also means that we can test it more exhaustively, because the tests are running much, much faster and much more, it's a much more repeatable and consistent testing process. Continuous inspection essentially is the same principle, but for testing of code quality, looking for code quality bugs, like methods that are too long or classes that have too many responsibilities and so on and so forth. The idea is that we remove the bottleneck of code inspections and pull requests by, as much as we can, automating the inspections of the code, automating code quality testing, so that whenever we're planning to check in our code, we get a very comprehensive review of the code that we've changed, that's done essentially by the computer itself. It's not a new idea. It's an idea that's been around for a long time, but it has been gaining in popularity. As teams strive to become more agile, and particularly to deliver more frequently, the need to speed up code reviews becomes more critical. It becomes part of the bottleneck in our delivery process. So more and more teams are dipping a toe into this water. Some teams are very mature at it. Some teams have just started to do it. And what I wanted to do in this video is talk about and demonstrate a little bit the tools, technologies, and the processes involved in this thing called continuous inspection. So for Java, I'm going to use an example project. I'll show you the GitHub project that I'm using. This is what we call a spike in extreme programming. It's basically a proof of concept that was done relatively quickly. It's not a huge project, but it is not trivial either. There's quite a lot of stuff in there, and therefore I think it would make a good demonstration, because we won't have to sit here for 10 minutes waiting for the code to be analysed. And because it's a spike, because it was done just as a proof of concept, although there are tests and I've taken some care over it, I haven't taken as much care over this code as I probably normally would on production code. So there are likely to be issues with it, things that I've not really taken care of, so to speak. So if I was working on this project, making changes to it, what I would really like to know before I check in any changes I've made is whether there are any problems with code quality. And so I could just sit there and read the code, of course. I could do a manual inspection, but much quicker and more effective would be to have some tool do it for me, because that can go through a whole range of different coding standards and rules and apply it to all of the code and do it automatically, and therefore do it quickly and consistently and repeatably. So let's take a look at this code. This code, by the way, this combiner, if you're interested, this is a sort of a proof of concept library that I wrote for generating test data, automatic test data for parameterized tests for use in JUnit, from combinations and ranges, basically. So if you pass it in a bunch of arrays, it will generate all of the possible combinations of the elements in those arrays, or pairwise combinations if you need it to be more efficient, or it can also generate ranges, numeric ranges. I was going to get around to doing random as well, but I never did. Just a proof of concept, but it does kind of sort of work. Let's take a look at the code. Okay, so there we go. There's lots of code. It's non-trivial. And as I scroll through, you asked me to review this code as I scroll through it. Now, this is how, if you're doing them by eye, this is how you should do code reviews, by the way. You don't just read the code and go, it looks all right to me. You need to be fairly mechanical and methodical about it. So, for example, a class. What can go wrong with a class? Well, there's the class's name, for example. That can be bad in various ways. For example, it could begin with a small p, and therefore it will be named incorrectly for Java. Let's just undo that. What else can go wrong with a class? Well, it could be too big. For example, it could have too many fields or too many methods, or too many lines of code. So I might inspect each class and go, is it named according to our standards? Has it got too many fields? Has it got too many methods? Has it got too many lines of code? And whatever else that might interest us about a class. For example, does it reference too many other classes? So we look at the class and then we say, okay, but what about fields? What can go wrong with fields? Well, again, the field name could not be according to our standards, or it can be confusing or misleading or too long. And field types, and there's all sorts of things here. Private, could this be final, for example? The answer is no, because we're doing something to it. So there's a whole bunch of properties of a field that we could ask questions about relating to our coding standards. Same goes for methods and method parameters and statements and lines of code and blocks of code and expressions. And basically, as we break the code down and we methodically go through it, class by class, method by method, field by field, parameter by parameter, statement by statement, and so on and so forth, to sit there and go, well, which of our coding standards apply to this thing in code? And of course, to do that methodically for all of it, let's say I've changed 100 lines of code, it's going to take a long time. So naturally, we don't do it. We just look at it and go, oh, it looks all right to me, or I don't like that. Now, a very experienced developer will probably pick up more than a less experienced developer, but still, if you ask me to review this code just by reading it, I guarantee you that if I was to then run an automated code analysis against it, it would spot a lot more than I did, a lot more. So there has that advantage to it. Now, if I wanted to analyze this code, as it turns out in IntelliJ, there is a built-in code analyzer. So if I were to just, let's go to our Analyze menu and say, look, I want to inspect this code. So I'm going to apply the built-in sort of standard template, the built-in rules, coding standards that IntelliJ will check for. We can, of course, customize these. We'll talk about that later. But let's just have IntelliJ inspect this code for me. So it's going to inspect all of the code. And it's found a bunch of stuff here, a bunch of interesting stuff, all warnings, so nothing major, but a bunch of stuff here. Let's talk about the structure of classes. So it's noticed, for example, I've got a field here combined that doesn't need to be a field. It's not being shared by any of the methods. It's only being used in one place. So there's really no need for this to be a field. And because it's a field, that can make it harder to understand, because you're having to look to see, well, what is that? What is combined? But also, it introduces potential for bugs. So we might decide, okay, let's inline that. And I can probably, let's try it. No, doesn't want to do that. Okay. There's the thing there. So combined. So we could have inlined it there, for example, and it wouldn't have made any difference to the functioning of the program. A bunch of other stuff. I think probably here I'm using something that's it's telling me for Java 13, well, we don't do that anymore. Something deprecated that might be removed at some point. So I might want to fix that. And there's a bunch of other stuff that I just didn't spot. I basically didn't spot. Now you will notice in this case, background compilation is picking up on many of these things as we're typing the code. So the feedback loops for code inspections are getting smarter, and they're getting shorter and shorter as our computers get faster and faster, and as compilers can do more and more. So IntelliJ, for example, in terms of background compilation, is building a model of the code, and it's doing all kinds of checks in the background, and it's alerting you as you're writing the code. Oh, we don't like that, we don't like that. So a lot of these rules are being applied iteratively as the code, or incrementally, if you like, as the code is being compiled in the background. And that is code review, whether you like it or not. And it makes a big difference. There was a time back in the bad old days when I worked in C or even in COBOL, where you literally had to sit down and read the code to look for things that we now expect our compiler to pick up on, that are not about whether or not the code is syntactically well formed, or whether it will compile, or whether it is good code, and those rules get smarter all the time. But we can also, as a sort of a batch job, run an analysis on our code and get lots of feedback. Now, there's also lots of feedback here about things that I don't necessarily care about. There's another one there about unboxing, for example. So the bunch of stuff here that I don't necessarily care about. And you'll see here as well, a little button's popped up. So not only can compilers these days, as well as compiling our code, actually analyze the code in the background to see whether or not it breaks any coding standards, it can also then suggest. So you know those little shortcuts you can take when your compiler says, oh, a little light bulb pops up, and you click on the light bulb and it can do it automatically for you. So that's pretty advanced stuff, considering what we used to have 20 years ago plus. So it's great. But there is a bunch of stuff here. I'm actually not bothered about this. And IntelliJ has a lot of built-in code rules for Java, some of which I agree with, some of which I don't care about, and some of which I disagree with. But we'll talk about that when we talk about rule sets and custom rule sets in a while. So the basic idea of continuous inspection is, as much as possible, we automate the testing of code quality, of inspecting code, so that we're getting the machine to look for problems for us, which it can do as a batch job when we, for example, use the analyze menu here. And there's all kinds of analysis it can do. Where are we? Nope, it's gone. There we go. Using the analyze menu. And as our IDEs and our computers get faster and faster, we also find that it can do that in the background, and it can alert us in real time to problems with our code quality. And that's great if you're working on a team where people are in the habit of using these tools. In the same way that if you're on a team where people are in the habit of always running the test before they check in their code. But alas, life isn't like that, with the best will in the world. So we might decide that we want to have a sort of a last line of defense. So we might decide that as a kind of a final check, we would want to build a quality gate into our automated build process. So as well as having a gate that runs our tests, because we can't trust developers to always remember to run their tests before they check in. So as well as having a quality gate that runs all of the tests as part of the build process and fails the build if any tests fail, we could also incorporate our code quality checks into the build process so that if we get any blocker issues, any major issues with code quality, we can actually fail the build, or we can throw it back and alert them, warn users about potential problems and so on and so forth. So I'm going to show you another tool now for Java. There's a bunch more. We'll take a look at the list in a minute. But I'll show you another tool for Java. I can run this at the command line. Just bring up my terminal. So you may have heard of a tool called Sonar Cube. Now, Sonar Cube is not a Java-specific thing. You would like to be... There we go. It's not a Java-specific thing, but it is very popular in the Java community. And it does a job that is very similar to what the code analysis tools that are built into IntelliJ do. But it also helps us to manage this whole process of continuous inspection, and I'll show you how. So I can run, as a Maven plugin at the command line, a Sonar analysis. So it will analyze the code in my combiner project, and it will produce a report. So I'm just going to do that now. Now, it's a little fiddly. Some of these tools have a bit of a learning curve. What I've actually done is I've got it in a little Windows batch file here. So I'm going to run this Maven goal here using a specific version of the Sonar Maven plugin, because whenever I try to run the general one, it doesn't work. So I'm using a specific version of the Maven plugin that runs Sonar code analysis. And it's going to upload the results to a shared web server, the Sonar server, where I have set up a project called Combiner for this already. You can see the location of the server, the URL of the server there, and there's a little security key there because it's on the web, as it were, because it's on a server. We don't want to be spammed, or we don't want people to be attacking our Sonar server. So there's a login there. We've got a key that we need to use. You don't need to worry too much about the details. All we need to know is when I run this batch file, when I run the Sonar plugin with Maven, it's going to crunch the code. It's going to build a model of the code, an abstract syntax tree of the code, and then it's going to apply a bunch of checks against that model to enforce a whole bunch of different rules. So let's run that, and hopefully that will work. Taking a little while, of course, as we would expect. It's crunching through the code, so it took a little longer. But that's because it's not just doing more analysis than IntelliJ. It's also going to upload all of those results to to a web server. Okay, so it's done it, and it should really, at this point, give us a URL for the project on our local little website there. So Sonar is running its own web server, and we can go to that and take a look at our results. Now, this is a new analysis that I've done. I've not really made any changes to the code. So here what we do is it's basically showing us issues that it's found with code that we've changed, new code basically, or code that's been part of the commit that we've done, and then also an overall picture of our code. This is the one we're particularly interested in, but I haven't made any changes. Let's look at the overall code. And very, very similar to the results that we were getting from IntelliJ. Different kinds of issues of different kinds of severity. Let's take a look. The code smells that it's raised. There's a few there. Okay, so we've got, for example, we've got a local variable here. It'll show us the code that has the same name as a field. That presents all potential risks. So I might want to rename that local variable to remove the risk of getting them mixed up, which could introduce bugs, or certainly will make the code harder to understand. So a similar kind of thing. It's raising a bunch of issues, and it can do that on code, making a distinction between all of the code and code that's been changed or added in our last check-in. So that's quite useful. So maybe working on a legacy system when we know the code's a bit rubbish, but we can at least say, yeah, but we're going to apply our standards to new code, right? So the tool allows us to do that, to to apply the rules to code that's changing or being added rather than all of the code. Now, it does this analysis, and that's great. But what else can we do with that information? Well, we have this idea of quality gates. So if we're going to incorporate this into our build process, our continuous integration process, for example, we can specify policies about what to do when when certain rules are broken, or when we reach certain thresholds, if you like, in the analysis. So now here's a bunch here about test coverage. For example, it can analyze test coverage files, and we can have a rule that says, well, now I happen to think that 80% is low. So on new code, I would say, no, it's got to be maybe 95%. Duplicated lines of code, I would say, yeah, as few as possible, please. So I kind of agree with that. Maintainability rating, well, that's a kind of an overall metric for the maintainability of code based on its complexity and other factors. You don't need to worry too much about that, but the general consensus is that it needs to be A, it needs to be gold star, please, new code. And then there's some security issues and other things that it can spot as well, which is very useful. Now, here's the thing. If you're working on a team and you're using a tool like Sonar Cube or one of the many other tools that are available, the biggest mistake I've seen teams make is to just take the tool and accept out of the box, these are the rules and these are the quality gates, these are the policies when we break the rules. What happens then is teams inevitably, first of all, let's take a look at the quality profile here. This is the rule set, the set of code rules for Java. There we go. So we look at the built-in rules, the Sonar way. Now in total, there's 555 built-in rules, of which 390 are switched on. That's a lot of rules, and the tendency is that these tools will generate, therefore, a lot of noise. And also they will generate a lot of false positives, that is, things that the folks who wrote these rules for Sonar think are bad that we maybe don't agree with. And also, there will be omissions from this. There are things in this rule set that I think are bad that aren't included at all. So the out-of-the-box experience, generally speaking, is not where you need to be. Where you need to be is in a situation where your quality gates and your quality profiles, your rule sets, are the ones that you, the team, have designed and agreed on. So, for example, I can create my own rule set here for Java. So I've got a couple of active rules here. Let's take a look. Activating more. And I don't want to see them all, so let's just... I'd quite like to just see the active ones, please. Available since... Where's the thing for active rules? Can't find it. Okay. No, that's not very helpful. Okay, what I'm looking for here are rules that are... brain overload, yeah. Rules about complexity. Okay. And we might have a rule here that says classes should not have too many methods. I agree. So let's activate that rule. Now you'll see now that it's not just switching that rule on. It's actually giving us some options here. So for example, do we want to include non-public methods, private methods? Well, I think yeah, because we're talking about the size. Now, it's saying here that the maximum threshold they've set, 35 methods. If I had 35 methods in a class, I would think there's a very, very strong possibility that that class is doing multiple jobs. So I think actually maybe 10 is kind of my limit. Now, I'm going to set that there and activate that rule as part of this quality gate. So I can apply this profile with all of my rules and the policies that I'm going to set up in a minute to my projects here, so that whenever we're doing a build, essentially, it will apply my rules with my tolerances, my settings, if you like, to my code. And that's very, very important that the team agrees these are our rules. You don't want hundreds and hundreds of arbitrary rules because there's nothing more annoying than being presented with a big report that says all these things are wrong, and you're looking at going, I don't really care about that, to be honest. And what you want is a set of rules that you've agreed on, and chances are there'll only be maybe a couple of dozen of them relating to the stuff that really matters. Remember, this is a last line of defense. So there are all our rules. Let's take a look at our project there. That's our combiner project. And we can settings. So what quality profile do we wish to use for this? Java, we don't want to use the Sonar way. We want to do it the codemanship way. Okay. Do I need to? Okay, yep. And in terms of quality gates, let's create a new quality. Yeah, well, I've created one there, the codemanship gate. So I'm saying if we raise any critical issues, there shouldn't be any critical issues at all. So if there are any at all in new code, it will fail the build. So that would be my policy essentially. So you set up a quality gate there. You set up your own quality profiles, and that might include writing custom rules. So as I said, there may be things in code that we think are a problem that they don't have a built-in rule for, or a rule that works the way we want it to work. And this is where the design process comes in. It's an evolutionary, iterative process. So if we go back to our code, for example, let's take a look at our combiner class here. This is where code reviews come back in. So what I'm proposing, if we're doing continuous inspection, this continuous automated checking of the code, is that that's not a process that you're going to get right first time. You're going to need to get into a room with the other people on your team, with the other developers, and look at your code and review it and ask for each part of the code. If anybody has anybody flags anything up, like I'm not happy about this, or I think that's a problem, we try to reach a consensus within the team. First of all, a shared understanding of what the problem is, then a consensus on how big a problem it really is, and then a consensus on what to do about it. Is this something that should fail a build? Is this critical or a blocker? Is this something we should warn about? What's the policy here? And then we incorporate that. We build that into our continuous inspection process, day after day, week after week. So you might on a regular basis be getting into a room, maybe mob programming, for example, and looking at real code and reviewing that code. And this is the equivalent of exploratory testing. So we have a whole bunch of automated code quality checks, but what about the code quality issues we didn't think of? Same idea as exploratory testing in agile development. Yes, we've got a whole bunch of automated tests, but what about the test cases we didn't think of? What about the examples we didn't think of? So the whole point of a code review now is to look for example code, to look for examples that we can use to drive the design and the implementation and the management of our continuous integration platform. And that might involve cutting real code, writing your own custom rules for Sonar, for IntelliJ. I think you can do it as well for many of these other tools, which we're going to take a look at now. So here's a wiki page, a list of tools for static code analysis. This is our section on Java tools. You'll notice that Sonar is not mentioned here, and that's because it covers a whole bunch of languages. So really, there's a whole bunch of languages here that we need to worry about. Check style for Java is very, very popular and open source. Another one that's very popular is find bugs. And these have very good integration with lots of other tools as well, including SonarQube. JArchitect is one that is a port of a .NET tool, so it's actually written in .NET. It's one I've used quite a few times as well, both for .NET projects and for Java projects. And that, again, it does a lot of the things. We'll take a look at the website, actually. It does a lot of the things that we get from SonarQube and other tools. And you can see the little picture there that we're getting similar kind of overview in terms of quality gates and rules and et cetera, and again, like these other tools, you can code your own rules, either using Link in .NET in C#, for example, or in its own built-in language, the code query language. So they're all kind of along those lines, Some are very basic, they just do code analysis. Some, like JArchitect and Sonar Cube, are more sophisticated and they allow you to manage rule sets and manage the process and apply code rules only to new code, apply it selectively and apply all different kinds of information and build in other analysis tools and other data from other sources like test coverage data and stuff like that. So some are more highfalutin. The more highfalutin they are, usually the bigger the learning curve. I must warn you about this. This doesn't come for free. This requires quite a significant investment. The good news is once you've done it for one project or one product, a lot of it can be reused for others. So won't happen overnight. You've got to start somewhere though, maybe just with something simple, with some basic out-of-the-box rules, and then start iterating that, getting feedback from its use. Now this is where the rubber meets the road, is how these are used. A lot of these tools will produce metrics. And once you start producing metrics, managers will want to see those metrics. And they'll start using these reports as a tool to beat, as a stick to beat the team with. Keep managers away from these tools. These are tools for developers to tell us what's wrong with our code. They're testing tools, not metrics tools. It's important to understand where the problems in your code are. And it's important also to have a call to action. For example, if your class is too big, maybe you should split it into 2 classes and so on and so forth. And as we've seen, some of these tools have that built in now. And they can do it for you within your IDE, like Visual Studio can do that, IntelliJ can do that. So there's a lot of good stuff available, but this is for developers to find and fix problems. And it needs to be able to tell us which problems are the most critical, but the idea is to stop them from getting into the code in the first place. That's the whole point of inspecting code continuously, just like the whole point of testing code continuously is to stop bugs getting into the code. Now, last couple of thoughts about continuous inspection. The first one is about whose rules these are. It's very, very important to get buy-in from the team. In fact, it's critically important to get buy-in from the team, that these are the team's rules, that they're not being imposed or just inherited. They're just the rules that came with the tool, or they were the rules that the last team used, or whatever. It's very, very important the team builds a consensus. Mob programming and code reviews, getting everyone around a computer and looking at real code and having real discussions with real examples must be a critical part of that process, and it needs to be a shared understanding and a consensus, at least a majority consensus, about what those coding standards are and how they will be implemented. The other point I wanted to make is about legacy code in particular. So you arrive on a project and the code is rubbish. Classes hundreds, maybe even thousands of lines long, and methods with 50 parameters and all sorts of terrible, terrible things going on in that code base. You know it's crap. You know it's crap code. You don't need to be reminded that every time you run one of these reports. So if you're working on code that has low quality or has quality problems that you know about, aim for a rising tide. That's how I call it. Aim for a rising tide. It's a good sort of rule of thumb. So figure out where the code is now. This is where all the bodies are currently buried. And then with each new check-in, at the very least, no more bodies. Bury no more bodies. The code must get no worse. So set the bar where it is. And then if anybody tries to check in code that makes it worse, that makes a long method longer or a large class larger, then you fail that build. You stop them from doing it. As code quality improves, you gradually start raising the bar. Gradually start raising the bar. So if your longest method is 300 lines long and someone refactors that and now it's 50 lines long, raise that bar to 50 lines. From now on, no longer than 50 lines. And on new code, genuinely new code, set the bar high. Set the bar high. So if this is a new class, there's no excuse for it being too big or for it getting too big. If this is a new method, there's no excuse for it getting too long. So with a bit of tweaking and a bit of ingenuity, get to a place on legacy code in particular where with existing code, existing classes, existing methods, etc., it gets no worse. And as it gets better, raise that bar. And on new code, apply the new standard. Test coverage must be 95%, and classes must have no more than 10 methods, or whatever your standards are, wherever you feel the bar should be set for new code. So there you go, that's continuous inspection. It's a whole can of worms. There's a whole skill set involved there in terms of using, for example, if you're writing custom rules, you're going to have to learn about language grammars and parsers and syntax trees and other stuff. It takes some yak shaving for sure to get these things up and running. You're not going to get it right first time, and you're not going to get it much better than wrong the second time, the third time, the fourth time, the fifth time. Gradually getting it less wrong, and with more and more experience you will get better. I promise you, you will get better and better at this, and the results you will reap from that, I've seen the results between teams before they adopted continuous inspection and a couple of years after, and the difference is really quite profound. The quality of the code is way higher. It's a lot higher, because these tools are picking up a lot of stuff that pair programming and particularly manual code reviews tend to miss. But most important of all, it does that without slowing down the team. So you're achieving very high quality, very clean code without creating bottlenecks because of code reviews and manual inspections and all of that stuff. So there you go. I'm not going to lie to you. This is not a trivial thing to get to. Going to require some work, it's going to require investment, and that's why 4 out of 5 of you watching this video, I guarantee it, you won't do it. You won't get there. But for those enlightened teams who are willing to make that investment, a whole world of much cleaner code awaits, plus a new set of skills that you might find translate into other things. Once you've learned how to write rules about code, you might get better at writing code that generates code, for example. For example, generating database persistence code or that kind of thing, or instrumenting your code or logging or that kind of thing. So once you start writing code that's about code, that's a whole skill set in itself, and it is a very useful skill set. So there's extra bonus here. There's bonus value. So there you go. That's continuous inspection. I'm a fan. I hope one day you will be too, if you're not already doing it. If you are doing it, let us know how you're getting on in the comments below. If you're not doing it, you're thinking about it, let us know in the comments below. There will be more videos coming, so ring the bell for notifications and subscribe to this channel. Lots more to come.